The first property we have already seen. What is the general shape of ROC? In the case of Laplace transform, it is vertical strips in the S-plane. Now, what about the ROC of Z transform? Can we say that it is rings in the, or ring in the, and what is the reason for this? If you consider a signal xn, the condition for existence of Z transform is this one. And in the Z plane, if you consider, if it converges at some point where this is R, if you consider any point along the circle of radius R, that will also be in the ROC, isn't it? So we can say that this is the shape of ROC. It is ring in the Z plane. Okay. Whereas in the Laplace transform, it is vertical strip. Here it is ring shaped. Okay. So that is the first property. The second property is that, again, if x of z is rational, then what about poles and zeros? If x of z is rational, can pole be inside the ROC? If you are writing a ratio of two polynomials in z, what is a pole? What is pole and zero?
So the points at which the denominator becomes 0.
Zero. Not the denominator. Yeah, we can say that poles are the roots of the denominator polynomial and zeros are the roots of the numerator polynomial, isn't it? We are expressing it as a ratio of two polynomials. So poles are the roots of this and the zeros are the roots of the numerator polynomial. So if let's say there is a pole at, let's say at P1, what about x P1? Is it finite? At P1 pole means this will be 0, denominator will be 0. So this will be infinite. Same thing we discussed in the case of Laplace transform. If there is a pole, that cannot be inside the ROC, isn't it? A pole cannot be inside the ROC. Pole is always outside the ROC. What about zeros?
Anyway,
Zero may or may not be in the ROC. Okay. Now, let us start with finite duration signal. Okay, tell me what is the property in the case of Laplace transform for a finite duration signal? What is the shape of the ROC? Finite duration signal, if the Laplace transform exists, then the ROC is the entire S-plane. Everywhere in the S-plane that converges. Here also it is the same. It is the entire Z-plane for a finite duration signal. The ROC is the entire Z-plane except 2 points. There are some exceptions here, so I will explain that. X of z is this one. Okay, I am writing this as expanding this summation. Okay, this is. Now consider a finite duration signal I'm saying that it is non-zero from, let's say, n1 to, it is non-zero in this interval, and it is zero outside that interval. Some signal, finite duration signal, its duration is from n1 to n2. That means it's non-zero only in that interval, and it's zero outside that interval. Now I have said that the ROC, if the Z transform exists, then the ROC must be the entire Z plane. But there is some problem here. Okay, let us start with okay, and this one. If n1 is less than 0, if n1 is less than 0, okay, first let us mark this. If n1 is less than 0, then what happens as mod Z tends to 0? Oh, sorry, there is an issue. If n1 is less than 0, yeah. If n1 is less than 0, then there will be always some term that is having positive powers of Z. Then what will happen as mod Z tends to infinity? What will happen to this summation? This one. Can we say that if n1 is less than 0, there will be always some term whose power is, that is Z to the power something, positive power?
Yes, sir.
There will be always some term here if n1 is less than 0. Then what will happen as mod Z tends to infinity?
XZ will diverge.
This will diverge, isn't it? This will be unbounded. So will that be in the ROC? So can we say that if n1 is less than 0, this is not in the ROC? This cannot be in the ROC, isn't it? Okay, I think first we can see the this case. If n2, what will happen if n2 is greater than, if n2 is greater than 0? This is a, remember we are considering a finite duration signal n1 to n2. If n2 is greater than 0, can we say that the summation always consists of some negative powers of Z? If n2 is greater than 0, there will be some term here. Now what will happen if mod Z tends to 0? Sorry, mod Z tends to 0. What will happen? Will it converge or diverge?
So diverge.
This will diverge, isn't it? As mod Z tends to 0, this will diverge because this is having negative powers of Z. This will diverge. So can we say that if n2 is greater than 0, then can this be in the ROC? Can this be in the ROC?
No, sir.
This cannot be in the ROC because if n2 greater than 0, there will be always some negative powers of Z in the summation. As Z tends to 0, this will diverge, and so Z is equal to 0 is not in the ROC when n2 is greater than 0. And when n1 is less than 0, same thing. When n1 is less than 0, there will be always some positive powers of Z in that summation, isn't it? When n1 is less than 0, because this one is x minus 1, x minus 2, like that. negative this is -1, -2, -3 like that. If n1 is less than 0, there will be some term here that is having positive powers of z. Now what will happen as mod z tends to infinity? This term will converge or diverge? This summation? If we have a signal x of n, its z transform is defined as this. X of z is this is the z transform. I am writing it as this one. I am expanding the summation, and these terms, these are the terms that are having negative powers of z, and these are the terms that are that contains, sorry, this is 2, positive powers of z. Okay. Now what will happen if mod z tends to 0? Which of these will diverge?
Negative powers of z.
Negative powers of z. This will diverge. And mod z tends to infinity. Which one will diverge? This one will
Positive
diverge.
powers.
And this will tends to 0. So this tends to 0 as mod z tends to infinity, but this will diverge. As mod z tends to 0, this will diverge, but this will converge, isn't it? And for existence of this z transform, this should converge. That means both these should converge. If one of these diverges, then this will not converge. That is what I am saying. If you consider a finite duration signal, let's say it is from n1 to n2. If n2 is greater than 0, then which point cannot be inside the ROC? N2 is greater than 0, then positive powers or negative powers will always be there. Which one? N2 is greater than 0 means, look, here it is x1, x2, like that. For example, this is 3. Then this summation contains terms up to x3, isn't it? If this is n2 is 3, let us consider an example. This is from 1 to 3. Finite duration signal from 1 to 3. So this is 3. So this will always contain some terms of negative, that is having negative powers of z. So that terms will diverge as mod z tends to 0. So can we say that this cannot be in the ROC? Can this be in the ROC? This cannot be in the ROC. Now same thing here. Let's say this is n1. If n1 is less than 0, if n1 is less than 0, there will be some terms that contains positive powers of z. So as mod z tends to infinity, this will diverge. So we can say that this cannot be in the ROC. So that is the property of ROC for a finite duration signal. The ROC is the entire z plane with two exceptions. If n1 is less than infinity, less than 0, then this cannot be in the ROC. and if n2 is greater than 0, this 2, the mod z is that z equal to 0, that cannot be in the ROC. So we can say that the ROC is the entire z plane except these two. And this may or may not be in the ROC depending on the value of n1 and n2. Okay. That is the property of a finite duration signal. Now for a right-sided signal, let's say it is starting at n1. It is 0 up to some point n1. So the property is similar to that of Laplace transform. If you remember the property of Laplace transform of a right-sided signal, what is the shape of the ROC? Right-sided signal. Laplace transform of a right-sided signal is what?
Right-sided.
It is right-sided, isn't it? The property is that if you consider the right for the Laplace transform, if the Laplace transform exists at some point, every point along this line is in the ROC. Not only that, all the points towards the right of that line is in the ROC. Same here, using the same argument, you can easily prove that if one point is in the ROC, we have already seen that all the points along the circle is in the ROC. If one point is in the ROC, all the points along the circle in the ROC. And if it is a right-sided signal, all the points outside the circle is in the ROC. That is the property. For a right-sided signal, the shape of the ROC is outside. It is outside a circle. Okay. And you can easily prove this. Suppose, let's say this is R0. Some point, this one, we say that at some point, this point, if you are given the information that this point is in the ROC, okay, that means this is finite. Now, if you consider any point outside the circle, let's say you are considering a point R1 here, and R1 greater than R0. Will this be converging? And here, because this is we are given the information that it is a right-sided signal from n1 to infinity, you can easily prove that if you consider any point outside that circle, then that will also converge. Okay. So the property of the ROC of a right-sided signal is that the shape is outside a circle. It is outside a circle. Okay. And one more question. Outside means is it up to infinity? What about this? Can it be in the ROC? It is outside a circle. My question is whether this ROC extends up to infinity or not.
Does it depend on the lowest value of the right side?
It depends on the value of n1. Because the summation starts at n1. And what is the condition? If n1 is less than 0, what will happen? If n1 is less than 0, then this is the summation from n1 up to infinity xn z raised to minus n, because this is a right-sided signal. It starts at n1. Okay. So if n1 is less than 0, can we say that there will be always some positive powers of z in the summation? If n1 is less than 0? then there will be always some positive powers of z in the summation. That means that summation that diverges as mod z tends to infinity. So this cannot be in the ROC. Okay. And the same thing for a left-sided signal. Left-sided signal means it is non-zero up to some point n2. It is non-zero up to some point. The property is that if one point is in the ROC, all the points along the circle is in the ROC. And if it is a left-sided signal, all the points inside the circle is in the ROC. Okay, the proof of this is straightforward. It is similar to the proof of this same property in the case of Laplace transform. So it is there in the textbook. Please go through it. Left-sided signal, all the points inside. Can we say that it is all the points, or some exceptions are there?
So for zero, we have to look for cases.
This may or may not be in the ROC, depending on what? That depends on what?
N2.
That depends on n2, because the summation will be now from n is from minus infinity up to n2 xn z raised to minus n. Okay, and if n2 is greater than 0, the summation always has some what? Positive powers or negative powers of z. If n2 is greater than 0, there will be always some term that has that contains negative powers of z. If there is some term negative powers, for example, if there is z to the power minus 1, what will happen as mod z tends to 0? This will diverge, or what will happen?
So for positive n2, it diverges.
Sorry?
For positive n2, it diverges.
Positive, that's what I am saying. No, why positive? Yeah, if n2 is greater than 0, there will be always some term that, with negative powers of z, negative power of z, and mod z tends to 0, that diverges. So this cannot be inside the ROC. So for a left-sided signal, the shape of the ROC is inside a circle, but this point, mod z, means we can simply write z equal to 0. This may or may not be inside the ROC, and that depends on the value of n2. If n2 is greater than 0, this cannot be inside the ROC. If n2 is less than 0, the ROC includes the origin also. Okay? Okay, now let us consider some examples. Let's take the... What is the Laplace Z transform of this signal? What? 1. And the ROC is? Is it the entire Z plane? Okay. It converges everywhere, irrespective of the value of Z. In the Z plane, it is a constant. And the ROC is the entire Z plane. Now, if you shift the signal, let's say delta n plus 1. What is the ROC? What is the, first tell me, what is the Z transform? You put it here. There is only one term in that summation, and that is when n equals what? When is this non-zero?
-1, n equal to
When n equals to -1. So this is, and what is the ROC? It is the entire Z plane except what? What will happen as Z tends to infinity? It diverges, isn't it? So this is not in the ROC. So it is the ROC is the entire Z plane except Z equals to infinity. Okay. And now if we shift it right, this is left shift, delta n minus 1. What is the Z transform? Is it this? In this, there is only one term, that is when n is 1. So this is n is 1, this is to the power minus 1. What is the ROC?
Every point except z equals to 0.
Yeah, every point except this point. Okay. So there is another interesting example in Oppenheim, that is this signal xn it is a finite duration signal a to the power n between n minus 1 and 0 and 0 otherwise. Okay, and given that a is greater than, let's assume that a is greater than 0. What is this Z transform? X of Z, if you put it here, this will be summation from 0 to n minus 1 a to the power n. Z to the power minus n. So this is, sorry, summation from 0 to n minus 1. Isn't it? What is the summation? Is it 1 minus a to the power n? Isn't it? Is it? 0 to n minus 1. So this will be n. Okay. We can simplify this. We can write it as 1 upon Can you tell me what is the ROC? What is the ROC? Which are the is it in a rational form?
Yes, sir.
0 and A.
So how many poles and how many zeros?
2 poles.
Sorry,
2 poles.
2 poles. Where are those
Z equal to
poles?
0. Z equals 0 and A.
Z equal 0 and a. How many zeros?
1.
1 0. Is it? What about this?
So one root.
1 pole.
1 pole.
1
So
pole.
one pole only.
1 pole only. Which pole? Which
Z
one?
equals to 0.
0. That means you are saying that there is a pole here. What about this?
Sir,
Is
it
it-
could get cancelled from numerator.
It will get cancelled. And can you tell me what are the zeros of this? You must have studied. Have you studied this?
Yes, sir.
Yes. Nth root theorem. Tell me what are the roots of this? How many roots are there? It is nth order polynomial, so there are n poles, n roots. Which are those roots?
Sir, they would lie on a circle of radius.
So tell me the expression first. And for what values, k is from 0 to n minus 1, isn't it? These are the roots. Is it? There will be n roots, k from 0 to n minus 1. They lie in a circle of radius. What? When k is 0, this is a. So there is a 0 here. They lie in a circle. Okay, this is not the exact location. And what is this angle? What is this angle?
Pi by
Pi by n.
It is 2 pi by n, isn't it? It is 2 pi by n. You can get from this. So there is a 0 here and there is a pole here that will get cancelled. So there is no, we can say that there is no pole here. There is only one pole that is at the origin. So what is the ROC? What is the ROC? What type of signal is this? Is it a finite duration signal? So it is the ROC is the entire Z plane except this Z equals 0 or and and infinity. This may or may not be in the ROC. In this case, what is the ROC?
Sir, everything except z equal to 0.
Every the entire Z plane except this point. Okay, that is the ROC. Okay, that's about a right-sided signal. For finite duration signal. For a right-sided signal, I think we have discussed this also. For a right-sided signal, the shape of the ROC is something like this. It is of this form, mod Z greater than R1. It is considered a circle of radius R1. It is exterior to that that outside that circle of radius R1. Okay. This is the shape of the ROC for a right-sided signal. And for a left-sided signal, and again, this is not guaranteed. This is in the ROC. It depends on what? For a right-sided signal means it is N1 up to infinity. So right-sided signal means it is 0 up to this point. The signal starts at non-zero value, starts at N1, some value N1. Then we can say that it is a right-sided signal. Now tell me, what is the condition for this to be in the ROC?
N1 greater than equal to 0.
It is N1. If N1 is greater than or equal to 0, then this will be in the ROC. Otherwise, it is not in the ROC. But it is, the shape is like this. It is outside a circle of some radius. And that radius, what is that radius of that circle? We'll discuss it shortly afterwards. Okay. And same for a left-sided signal. For a left-sided signal, it is inside a circle of radius, some radius. Okay. Left side, and again, this point inside, when we say that inside the circle, this may or may not be in the ROC. Left-sided signal means it is non-zero up to some value N2. So what is the condition? If N2, when this is in the ROC?
Less than equal to 0.
Less than equals to.
When it is less than equals to 0, then it is in the ROC. Okay. So that is the shape. And for a two-sided signal, we can say that we can always express a two-sided signal as a sum of a right-sided signal and a left-sided signal. So the ROC will be the intersection of this. Suppose for the right-sided signal, the ROC is mod Z greater than R1, and left-sided signal, it is less than some R2. So what is the condition for existence of that Z transform for that sum of those two signals? Does it relate?
R2 greater than R1.
If the intersection is there is some ROC only if R2 is greater than R1. Okay. Okay, that's about right-sided signal, left-sided signal. Now we can about this radius of that circle. Again, that property is also similar to that of Laplace transform we discussed already. Pole cannot be in the ROC. Okay, 0 may or may not be in the ROC, but pole cannot be in the ROC, inside the ROC. So if x of z is rational, if we can write it as two polynomials in z, then the property is that the ROC is bounded by poles. ROC is bounded by poles if it is a rational Z transform. if we can express it as a ratio of two polynomials in Z, then the ROC is bounded by poles. Now for a right-sided signal, for a finite duration signal, there should not be any pole other than at 0. This may be there may be a pole at this point. Other than this, there is no pole for finite duration signal. But for a right-sided signal, suppose there are some poles like this. Let's say this is the pole 0 plot. What is the possible ROC? It is a right-sided signal, so the shape of the ROC is outside a circle of some radius. Okay, that is the property, outside a circle. And the second property is that if it is a rational function, then it is ROC is bounded by poles. So can we say that which pole? Then tell me which of these poles will determine the shape of the ROC? If suppose there are 3 poles, which one of these poles?
So the leftmost.
The leftmost, or instead of leftmost, can we say that it is the outermost pole? It is the outermost pole, isn't it? So can we say that for a right-sided signal, the ROC is draw a circle through the outermost pole? Everything outside that, this will be in the ROC. Okay. Now for a left-sided signal, suppose there are, let's say, 3 poles like this. Pole is bounded by, ROC is bounded by poles, and the shape of the ROC for a left-sided signal is, it is inside a circle. So which will be the circle here? Is it this one? Can we say that it is a circle through that innermost pole? Here we have left-sided signal. We have to consider the innermost pole. And here, this is the outermost pole. Okay. So innermost pole and outermost pole. And again, it is inside this circle, but this point may or may not be in the ROC depending on the value of up to which point it is non-zero. Okay.
Sir, if a 0 is outside this region, then we will say that it is in the ROC or not.
Which one?
Sir, in case of left-sided signal, if a 0 is found outside the ROC.
Let's say this radius is R1. So we will say that ROC is inside the circle of radius R1 except this point.
And sir, if a 0 exists outside this region, for example, at distance R2.
Okay, some 0 is there. Then?
So we will write ROC is mod Z less than R1 or mod Z is less than R1 and also at that 0.
No. That is what I have explained in the previous class. XZ is, okay, this one. And you can watch the previous video. There I have given some examples. What is a 0? 0 is the root of this, isn't it? Root of this numerator polynomial. Okay. And what is ROC? If you write any expression, you can always find a root of that. If you express it as a polynomial, you can always find a root. But the problem is that ROC is the region where this expression is valid. Okay. So does it make any sense if you find the root outside that region where that expression is valid?
No, sir.
No. So that's why we say 0 may or may not be in the ROC. If this root is inside this region of convergence, it is okay. But it is possible that this polynomial can have have this polynomial can have roots outside this ROC, but that will not be inside the ROC because that expression is not valid here. Okay.
Okay, sir.
So it is we have to consider the region in which that expression is valid. Okay.
Right, sir.
Outside this ROC, this expression itself is not valid. So there is no point in finding the 0 there. Okay.
Yes.
So 0 may or may not be in the ROC, but poles cannot be in the ROC.